We'll now turn to Hartwig Busch. Sorry if I misspell your name. My German skills are not so good. Hartwig graduated from the Aachen University in 2000 with a degree in mechanical engineering, and he joined the Institute for Combustion Engine of RWTH Aachen to work in the field of passenger car diesel engines as a research assistant, and obtained his PhD in 2009. He worked at FEV and Jaguar Land Rover, and in 2014 took the role as a principal engineer for performance and emissions development in Coventry University. No, sorry. In
that
FEV.
was post at Jaguar Land Rover.
Okay, sorry, there are too many affiliations in your resume, but the floor is yours.
Yeah, thank you very much for the kind introduction. Good afternoon, ladies and gentlemen. It's a pleasure to stand here to give a little bit of an outlook from a university and an engineering service provider about the pathways for light-duty diesel engines towards nearly impact-free operation. At first, I'd like to give a brief overview of my talk this afternoon. At first, I'd like to give a short introduction about the current situation. Then I will give an overview about future legal requirements and key market demands. And then I will give hopefully a somewhat positive outlook for future diesel engines with respect to possible technical innovations and future powertrain configurations before I close the talk with a summary and an outlook. If you look at the current situation, we've heard it before in talks from BMW, that the electrification is a growing segment. But we need to take into account, if you look at the overall production numbers of internal combustion engines over the next 22 years, this is still an enormous amount, in the range between 90 and 100 million units per year. And that just underlines the importance of the internal combustion engine and also the continued investment into the development of the internal combustion engine. When we look at the area where the growth is, the main, or put it what we also see is there's a significant increase in light-duty vehicles without an internal combustion engine over the years. But in the end, the main key message is for the foreseeable future, there is a very high share of internal combustion engine vehicles around. If you look at the current situation of the diesel market share in Europe, what we can see is that over the years up to 2015, before the diesel scandal, the market share of diesel-engined light-duty powertrains was fairly constant, around 50%. In Europe. And then after the diesel scare and after the diesel scandal and the increasing discussion about access of diesel engine cars to urban areas and driving bans, there's been a very steep decline since then. And for example, in Germany, in November last year, the diesel market share was only 34% compared to values around 50% before the Dieselgate scandal. And this is a universal trend across Europe, with the only notable exception, which is Italy at the moment. But what we've also heard from BMW, this is not without consequences on the CO2 emissions. So what we see, or what we saw last year for the first time, is that the fleet average CO2 emissions of new cars increased compared to the year before, and that is a direct link with respect to the diesel market share. And if you look at what that means, if we have a look at certified fuel economy figures and real-world figures, which are here displayed as the lines, and the certified figures are displayed as the bars, we can see there is a very significant there's a very significant difference in fuel economy between diesel and petrol cars, and this is fairly significant. Yeah, this is in the range of up to 40% if you look at volumetric fuel economy. Yeah, and if you look at CO2 figures, yeah, normalized to an identical vehicle weight, yeah, we see roughly a CO2 advantage for diesel engine powertrain in the range of 28%. Yeah, and that shows that the diesel is an extremely important contributor to meeting future CO2 emission legislation, and therefore it's vital to keep this engine and powertrain option attractive. And it's really key to keep in mind, despite lobbying from specific groups, yeah, that diesel engines don't have a benefit in terms of CO2 emissions, which is thermodynamically wrong, and it's also proven, yeah, for example, by publicly available data, yeah, whether it's from Spritmonitor, yeah, or let's say before the talk, I had a quick look at emissions analytics EQ data for a BMW 2-liter engine, yeah, and there's a very clear step change, yeah, from petrol 2-liter engines to diesel 2-liter engines, yeah, and the diesel has got that very clear advantage. And it's worthwhile to keep that advantage alive and on the market. So, if you look at legal requirements, so when we look at legal requirements, and I specifically added also Chinese emission legislation here, because China in terms of light-duty emission legislation at the moment is moving a little bit ahead. So what we can see, yeah, if you look at China 6B emission legislation at the bottom, yeah, which will be introduced from July 2023 onwards, yeah, a NOx emission target of 35 milligram per kilometer. And this is combined with a few other quite challenging emission regulations. I mean, the conformity factor for this is 2.1. Yeah, so that means real-world NOx emission level, or the real-world NOx emission level is 73 milligram per kilometer. And there are other aspects there, taking into account a specific geographical and topological boundary conditions in China, such as high altitude and a broad temperature window. And China enforces the very stringent US OBD regulations. Yeah, so if you look, yeah, what that might mean for a future Euro 7 scenario, yeah, in terms of extended environmental conditions, yeah, so the altitude range might be further expanded. And if you look at the Chinese altitude range, yeah, that means also there's a significant increase in the temperature range. Yeah, so that means there's a very big task upcoming in terms of future emission compliance for the light-duty diesel engine. And then we need to have a look at emission compliance in real driving conditions. Yeah. In a study which we did with a catalyst supplier, yeah, we had a look at different driving cycles. Yeah, at the top, yeah, there is a typical RDE cycle. At the bottom, the WLTC cycle. And in order to have a view on the most challenging condition, yeah, basically the task was to investigate specifically the urban cycle, yeah, of the RDE cycle, but over an extended period of time. So, and that means, yeah, that the challenges on the low temperature activity of the exhaust after treatment system is increased. Yeah, and just to highlight that importance, yeah, if you look at the frequency of the temperature achieved, yeah, for the different cycles, yeah, we have got the catalyst temperature upstream, the LNT on the x-axis, and the relative frequency on the y-axis. Yeah, and if you look at the marked city cycle, yeah, we can see that basically the vast majority of operating points are below 200 degrees C upstream the LNT. Yeah, and the average temperature in this very challenging cycle is on average only 175 degrees C. So a very big task, yeah, to achieve good conversion efficiency under these conditions. Yeah, if you compare that, for example, to the WLTC or a typical RDE cycle, we see that those cycles are much easier to work with from a thermal management point of view. Yeah, and just to highlight that, what that means, yeah, in such a city cycle conditions, yeah, because it's relatively low distance, yeah, we need to be able to light off the catalyst very early on in the cycle, yeah, in order not to violate the legal emission limit just because of emissions during the warm-up. Yeah, and there we can also see, let's say, an indication of the technical solution, yeah, which we proposed, yeah, for that, which is a combination of a closed-coupled NOx trap combined with a closed-coupled SDPF and an additional underfloor SCR system. Yeah, so it's a three-stage NOx reduction system. And then in combination with an appropriate thermal management strategy, and in this, let's say, very low-speed urban driving cycle is associated with a relatively small fuel economy penalty of only 2 to 4%. If you look at other technical innovations in powertrain and future powertrain configurations, yeah, we have, let's say, as I said before, we have this three-stage DNOx system, yeah, with an LNT, closed-coupled SDPF, and an underfloor SCR. The advantage is the combination of different NOx after-treatment devices increases the temperature window in which a highly efficient NOx conversion can be achieved. However, yeah, when you look at such a system, yeah, it's not just adding the components to the system. A very high degree of optimization has to go into the layout of the system, for which I will give a few examples. One key element of an optimization is the selection of the wash code for the LNT. Typically, or the starting point is typically the wash code formulation of a normal standalone LNT, yeah, which is quite common on Euro 6B vehicles, which has got a relatively broad temperature window. But if you take into account that the LNT has to operate, or that the LNT operates in combination with an SCR system, yeah, we can optimize the LNT for increased low temperature activity. Yeah, so to give the system an overall higher capability. Yeah, and also what has to be kept in mind that with the increased low temperature activity, the robustness of the system over full useful life against desulfurization events or against DSOX events has to be improved, and that is possible with state-of-the-art wash codes for LNTs. Another aspect which is extremely important for such a system is the uniformity of the ammonia distribution on the SCR catalyst. And basically, as part of this study, yeah, we investigated or we optimized the mixer. We optimized the mixer design to take into account optimum ammonia distribution and low pressure drop. And in the end, yeah, the final optimization achieved more or less a nearly fully homogeneous ammonia distribution under different operating conditions, yeah, from low load up to high load, yeah, with a relatively small pressure drop increase. But it has to be taken into account that also the diameter was reduced in that case due to package reason of the exhaust after treatment system. So this is also very important here to maximize the conversion efficiency of the SCR systems. I mentioned before, yeah, thermal management, especially for urban driving conditions, is a key element. And when you look at it, or one example from a study we had is when we looked at the benefit of an electrically heated catalyst. What we can directly see that the introduction of electrically heated catalyst systems here in a TFL cycle at 3 degrees C has the potential to reduce NOx emissions or tailpipe NOx emissions by 60%. And in terms of the trade-off between NOx reduction and CO2 increase, an electrically heated catalyst is actually favorable. Is actually more favorable compared to conventional heating measures. We don't have to do this with an electrically heated catalyst. Another way to enhance the capability of the engine, especially under heating operations, is the introduction of valve train variabilities to assist heating. Don't want to go through all the details. We've investigated various different solutions. From from just exhaust cam phasing, to the introduction of a Miller timing to cylinder deactivation. But in the end, what is important is that for a constant tailpipe emission in WLTC, you have the chance, with the introduction of valve train variabilities, to significantly reduce CO2 emission, because you can achieve a more efficient heating mode. And also, what is very important, if you look at such a combined system with LNT and SCR, is a smart management of all exhaust after-treatment components involved. So basically, we can divide the storage management of the LNT into 3 different phases. So in the first phase, when the engine is cold and the after-treatment is relatively cold, the lean NOx trap has to do the main conversion load for the NOx emissions. But as the whole after-treatment system gets warmer, the regeneration frequency of the lean NOx trap can be reduced, and thereby the CO2 penalty of the LNT can be reduced. However, it is important that there's still some level of NOx storage management in the LNT in order to maintain a favorable starting position for the next cycle after the engine is shut off. If you look at the whole powertrain system, just to give an example of the FEV EcoBrit system, where 48-volt BSG system and an electrically driven compressor was integrated into a 1.6-liter base engine, including an energy management. If you look at the potential which we have with such a technology combination, here exemplarily shown for an acceleration from 30 to 60 kph in 4th gear. If you look at the high-level results in the bar chart, we can see that the introduction of the BSG and the e-compressor allow a significant improvement of dynamic dynamics, which is to be anticipated. But what's also very important is that the NOx emissions during this transient maneuver, due to the, let's say, improvement of the response of the air system and due to the assistance of the, due to the torque assistance by the BSG, is significantly improved. It was also noteworthy if you look at the operation with the e-compressor, due to improved gas exchange work under these operating conditions, we do see also an improvement in specific fuel consumption. If I come to a summary and an outlook, which I will show in 2 stages. On the one hand, if you look at NOx emissions, I simply want to spread the message that the diesel engine has got a tremendous development potential to really go down to minimum NOx emissions, yeah, which are in line with the best petrol engines, yeah. But this requires a combined effort with respect to optimizing the combustion system, exhaust after treatment system, introduction of heating strategies, hybridization, and smart control strategies, yeah. And based on a car, yeah, mid-size vehicle, yeah, NOx emissions in the range of 16 milligram per kilometer under real driving emissions are possible. But also, yeah, we need to have for the diesel engine a story with respect to fuel economy. And if you look, yeah, starting from the very left-hand side, yeah, WLTP for a non-hybridized system, yeah, the base engine, what we see up to 2025, has got a fuel economy potential of roughly 6%, and with, let's say, a dedicated effort towards right sizing, up to 11% fuel economy is up to 11% fuel economy improvement is possible. And if we then look at the next group of bars, yeah, when we look at WLTP in combination with 48-volt hybridization, yeah, we can see that that benefit is even further increased. And most importantly, yeah, we can maintain this fuel economy benefit even under real driving conditions. Yeah? And only if we look at the RTS 95 cycle, which is an extremely aggressive driving cycle, yeah, that there is a, let's say, somewhat small deviation from the WLTP result. And the final statement, yeah, if you move to the blue bars or to the group of blue bars on the right, at low temperature conditions here, this technology enhancement allows a significant fuel consumption reduction even under low temperature conditions. I hope I could give you, let's say, a somewhat positive outlook on the future potential of diesel engines, and I want also to take the opportunity to do a little bit of self-marketing. For people who have got flexible calendars, yeah, we'll have a conference near Coventry next week where we will go further into the discussion of these topics about future development potential for light-duty diesel engines. Thank you very much for your attention.